Hello everyone, welcome again in Eng-Man YouTube channel. So in this video, we will try to perform nodal analysis in a gas well that will be equipped with foam lift. Alright, so we will do the analysis using Prosper software, and we are now inside the Prosper, so you can follow me. First, we go to the section. Okay, for the fluid, we will select dry and wet gas, method black oil. All right, so for the separator, single stage separator, PVT warnings, disable warning, and for the water viscosity, use default correlation. All right, and for the water vapor, we use this one, calculate condensed water vapor. All right, and then for the flow type, tubing flow, of course, and then for the well type, producer. For the artificial lift method, later on, we will go to foam lift, but first we will start with natural flow. So we select none. All right, so you can also type in the company, field, location, well, and so on and so forth in these sections. And for the calculation type, we will go for the offshore, model rough approximation. And then for the range, full system, brine properties correlation default, type cast hole, send control none, and for the inflow type, we select single branch. Okay, from here, we'll go to PVT, and okay, we can go for the PVT section. You can follow my data for the gas gravity 0.58, separator pressure 200, PSIG, and then for the condensate gas ratio 1, and for the condensate gravity 50 API. So it, of course, it's condensate, it's light, so the API degree will be high. Water gas ratio, it's quite high, 100 stock tank barrel per day per MMSCF. All right, and for the water salinity, let's assume 100,000 ppm, mole percent of H2S0, carbon dioxide 0.5 in percent, and for the nitrogen 2. And we will model the gas viscosity using Lee et al. Correlation. All right, and now in this data, other data option, we will use default correlation. Okay, and then for the water vapor, calculate condensed water vapor. And then for the reservoir data, you can follow me. For the reservoir data, reservoir temperature will be 165 with reservoir pressure of 1200 PSIG. Okay, and then for the water vapor data, it will be calculated automatically, but you can check the water vapor plot by clicking this button. Okay, so you can see the saturation WGR, water gas ratio, against pressure for several temperatures. Right, you can see we go from 60 degrees, 77.5, and then 95 through 165 degrees Fahrenheit. All right. It's an important plot, of course, WGR, water gas ratio against pressure for each temperature. So it's an important plot for us in this analysis. Okay, done. And we can calculate, and we provide the range. Let's say for the temperature, we will go from 60 degrees Fahrenheit through the reservoir temperature, 165. Number of steps, 10. And for the reservoir pressure, we go from 200 maybe through the reservoir pressure. Number of steps, 10. Gas viscosity using Lee et al. And we calculate. Okay, this is the results. important results: temperature, pressure, gas density, gas viscosity, gas formation volume factor, Z factor, water density, water viscosity, water formation volume factor, including interfacial tension, okay, IFT, pseudo pressure, okay, this is the liquid gas IFT, oil gas interfacial tension, and so on and so forth. You can also plot, or first you can copy and paste on your spreadsheet, and then you can plot, let's say, against the pressure. So we have several temperatures, okay, and for the temperature of the reservoir temperature, let's say we want to check the gas formation volume factor, so this is the plot. What about the gas viscosity? This is the plot, right? And then remove all pseudo pressure, all right, and the interfacial tension, liquid, oil gas, water gas, oil and water. All right, so it's a very, very important analysis, the PVT analysis, of course. So we have done the PVT analysis for this gas system, right? Okay, and then including gas density. All right, remove all. Okay, done, done, done. All right, so we have completed the PVT analysis for dry and wet gas system, right? You can see. And from here, we will go to our IPR data section. Okay, so you can follow me. For the reservoir model, we will select the, we can see several models here, right? Very important. And we will go for the petroleum experts. You can see the description, the explanation for this model in the help section of the Prosper software. All right, so we will select petroleum experts. For the mechanical or geometrical skin, we will enter skin by hand to make it simpler. Okay, and then you can follow me for the reservoir pressure. Of course, 1200 psig, the reservoir temperature, this one. Water gas ratio, quite high, 100. With condensate gas ratio, 1 stock tank barrel per day. I mean stock tank barrel per MMSCF. Compaction permeability model, no, to make it simpler, of course. And for the model data, you can follow me. Reservoir permeability of 25 millidarcies with reservoir thickness of 55 feet. Drainage area, 500 acres with DH factor, assuming a circular reservoir, cylindrical reservoir, so it will be 31.6. Wellbore radius of 0.350. Perforation interval, 55 feet. So we will open all the thickness of our reservoir. Time since production started, it is 50 days. Yeah, we assume with 50 days. And for the connate water saturation, 0.25. Okay, and reservoir porosity 0.15. Non-Darcy flow factor will be calculated rather than entered. Okay, so we will calculate. And for the beta factor method, original, permeability entered is total permeability. Okay, it's a total permeability. And we will go to mechanical or geometrical skin. We enter by hand. Let's assume 2. Skin factor of 2. Enable Wong-Clifford model, no. Okay, we can validate. The IPR dataset is valid, so we can calculate. First, we will get this number. And of course, the maximum flow rate or absolute open flow. Calculate. All right, so you can see the non-Darcy flow factor now is calculated. This is the result. and this one, absolute open flow, 13 mmscf per day, million standard cubic feet per day. Okay, and then we can plot results. The x-axis rate and y-axis, I'm more interested in pressure. Done. Right, so this is our IPR, inflow performance relationship. Of course, you can plot other variables, including temperature, right? Remove all first. You can also plot the total skin. We assume constant value of 2, of course. All right. It will be available if we make the analysis, make the data input more comprehensive. If you use, for example, gravel pack, right, you will have more skin in the completion or send control section. But for our analysis, the most important parameters is, of course, flow rate and pressure to make the IPR. All right, this one. And this is again the calculated data, the AOF, absolute open flow, and the skin. The skin is inputted. Okay, done. Done. All right, so we are now completed in the IPR section. From here, we can go to equipment data section. All right. We will input the deviation survey, downhole equipment, geothermal gradient, and gauge details. Edit. First, the deviation survey, you can follow me. 0, 0, and then this one. Okay. 2000. Okay. 2500. 2450. 3000. 2883. All right. And then for this one, 3500. 3300. 4000. 3721. 4500. Okay, and then 5000. 4560. 5400. 4900. You can plot. All right. So this is our deviation survey. We have a deviated well. Finish. Done. Okay, from here we will go to downhole equipment. Christmas tree at 0 depth. And then we will have tubing down to 1000 feet with inside diameter of 0.95 inches. Tubing inside roughness, this one. Okay, and then we have also subsurface safety valve with tubing inside diameter of 0.95. Yeah, let's assume it has the same tubing inside diameter. To make it simpler, you can also make it smaller, right? Because it's a valve and tubing down to 5000 with 0.95, tubing inside roughness the same. Okay, and then for the casing, this one with casing inside diameter of 6 inches. The same, the default roughness, and for the rate multiplier, all is 1. Okay, later on, if we install foam leaf, we will need to input this information for tubing outside diameter. All right, because we will involve annulus in our analysis. All right. Okay, from here we can click done, and then we will go to geothermal gradient with overall heat transfer coefficient of 3, and for the temperature at 0 depth 45, And then for this depth 75, and the reservoir depth 165. You can also plot, yeah, this one. Okay, and then we can click finish, done, gauge detail, no need. Okay, average heat capacities, we can click edit. Yeah, to check the average heat capacities, we can use the default numbers. Done. Okay, so we can check the summary. Okay, this is our summary, and we can click draw downhole. So as you can see, we will have Christmas tree and then tubing, and after that we will have subsurface safety valve, and again tubing. Okay, and lastly we will have casing. Okay, now from here you can click done. From here we can go to nodal analysis, right? This is our well sketch, well diagram. Now we will go to calculation to perform the nodal analysis. The top node pressure, the wellhead pressure in this case is 500 with water gas ratio 100. So the top node pressure itself is already high. So we will have maybe with this water gas ratio, we will suffer liquid loading problem maybe because we have high water gas ratio and high wellhead pressure. Okay, we will check that later. And for the condensate gas ratio is 1. Okay, and then the vertical lift correlation, we use this one. Solution node, bottom node, automatic geometric, let's say, and left hand intersection disallow. This one is no. Okay, we will check, and now we will calculate. Show calculating data. Okay. As you can see, we suffer nodal analysis. I mean, we suffer liquid loading problem. First, you can check this table. Okay, be careful here. We have gas rate, water rate, and if you move to the right, you will see maximum terminal velocity and terminal velocity flag. If we have yes, it means that we are under the terminal velocity, which means we are in the risk of liquid loading problem. But if we have no, it means that we have no problem with liquid loading issue because we have rate that is higher than the Turner rate. And you can see we have yes all over the place except the last one. And visually you can see the plot, this one, this flag Turner, 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 right? So it's a problem. That's why later on we will install with foam lift. Okay, so this is our condition. Okay, you can also check the plot. Right, this is our condition. You can also check this one, terminal velocity flag. Right, this is yes or no, 1 or 0. So this one is the yes. So below or on the left side of this section, we have liquid loading problem, and our operating point is on the left side. All right, on this terminal velocity flag. And on the right side of this one, we have 0 or no problem with liquid loading. So it means that if we flow at rate of 10 or 12 million standard cubic feet per day, we will have no problem with liquid loading. And below that, we will suffer liquid loading problem. We can maximize at this section. All right, so you can see we have liquid loading problem. So now we will equip our well, our gas well, with foam lift. All right, so we can click done. we can go to this one again, option summary. We will select artificial lift method, foam lift. Okay, done. Right, you can see we have this section now. Okay, we can open and you will have this foam input data. Okay, you can follow me. This we have surface tension and here we have foam density. Okay, and you can follow me. You can edit the value, surfactant concentration and the surface tension. We can use this value 0.02. Okay, and then 66. Yeah, you can use these numbers. Okay, and then the foam density, surfactant concentration, and this is the foam density, 0%, this one, and then 0.05%, this one. So as you can see, as we increase the surfactant concentration, the foam density will be smaller. It means our liquid, our fluid will be lighter, and it will make the reservoir pressure able to push the fluid from downhole to the surface, enabling our well to now to flow. All right. And also, if you increase the surfactant concentration, the surface tension will be lower. And this is the plot. Surface tension against surfactant concentration. So as you can see, as we go to the right, the surface tension will be smaller, will be lower. The same thing with foam density. We have foam density plot against the surfactant concentration. So if we increase the concentration of the surfactant, the density of the fluid will be lower. Right, so that's quite clear. From here, we can click done. Okay, let's check again the operation summary. Okay, dry and wet gas, black oil, this one. Okay, so far so good. Now we check this one, the downhole equipment, edit. Okay, so as you can see, click done, click done. Can check this foam lift system, foam lift, right? This one. So if we go to this system, foam lift, the window, it's actually the same with this one. Okay. Okay, this one. All right. We open again the equipment data section. Okay. All right. Okay, as you can see, we still don't have tubing outside diameter here, but it's important because we will have foam lift. So from here, we will go to done, this one cancel and cancel, close. In operation summary, you go to the annular flow. All right, annular flow, because we will inject the foam. Okay, and then it involves annular flow. Okay, annular flow has been activated. We go to here again, and for this one, edit, downhole equipment, edit. Nah, you can see now we need to input the tubing outside diameter. Okay, 1.125. Okay, with casing inside diameter, now it's important 3.958. Okay, and then this one again 1.125 with casing inside diameter of 3.958. with casing inside diameter 6. Okay, the same. All right, now we can check the summary, draw down hole. Okay, so as you can see here, we have casing in the upper section with inside diameter of this one 3.96. Done, done, done. All right, okay, so from here we will go to calculation system IPR VLP. Okay, and then for this one we can calculate first. All right, okay, this is our condition first. If we go to surface equipment correlation Bex and Brill, okay, now we go to the cases, open, and we go to surfactant concentration. Okay, click done first. I mean cancel. So for this one, we will go to, this is important, okay, the form homogeneous. Okay, calculate first. Okay, all right. So as you can see now, our IPR has been changed. Okay, because now we will involve foam. Okay, yeah, as you can see, the Turner velocity issue is only from 0 to maybe around 7, and now our operating point is here. Okay, now we go to cases, and now we will select this one. You can follow me, surfactant mass percent. We go from 0 and then 0.02. Okay, and then for this one, 0.13, 0.18. We vary the surfactant mass percent, the surfactant concentration 0.23. It is in percent, okay, 0.28, 0.34, 0.39, 0.545, and 0.5. Okay, we have several liquid foam, okay, surfactant mass percent as our varied parameters. Okay, we click done, and now we can calculate, show calculating data. Okay, we go to sensitivity plot. You can see pressure against surfactant mass percent. We change the variables. Rather than pressure, we will go to gas rate. Okay, so as you can see, as we increase the surfactant mass percent, the surfactant concentration, we will have higher gas rate. Okay, as you can see, this is interesting. Done. And we can go from here to see the IPR. Yeah, you can see the IPR is changed, but the change is not that significant. Yeah, here you can understand the limitation of this foam leaf, of course. So if we increase the surfactant concentration, yes, of course it will increase the flow rate, but we cannot expect a significant change in gas rate because this is foam leaf, this is surfactant injection. We cannot expect something significant change like what we have in electrical submersible pump, right? Because we involve mechanical equipment in the pump. In here we use chemicals. Okay, so it's very different, but still we have improvement if we increase the surfactant mass concentration. And then we can plot system plot, plot all cases, VLP, then the IPR, right? We have this one. And we can also check the terminal velocity flag. So as you can see, our operating point here is actually on the right side of the terminal velocity issue. So we will have terminal velocity issue from 0 to around 6.5 or 7 million standard cubic feet per day, but our operating point is higher than that Turner critical rate. So you can see, we can say that the critical Turner rate or the critical rate below which liquid loading problem will happen is around 7, but our operating rate is around 9 million standard cubic feet per day. So as you can see, we can maximize, yeah, around 8.5, 8.4. Okay, finish. All right, that's the analysis if we involve liquid loading problem. First, we run a nodal analysis for a well with high water gas ratio. Okay, we create the IPR using petroleum experts model, and we go without foam lift, without artificial lift, and we will suffer liquid loading problem as the flow rate is below the Turner critical rate. And after that, we equip our gas well with foam lift, and we vary the surfactant concentration, and we can see improvement in rates. And now our well can operate above the critical rate zone, which means that we are now free from liquid loading problem. All right, so I think that's all. I hope you enjoyed the video. I hope the video is useful. Thank you so much for watching, and see you again in the next Prosper videos. Thank you.